Today we're going to look at gravitational fields. We're going to be defining the idea of a gravitational field. We're going to explore and use the relationship for Newton's universal law of gravitation. We'll define and use the relationship for gravitational field strength, and we will interpret a field line diagram. That's two equations, some calculations, and some diagrams. The idea of a field is very common. We come across it in sports. A field is an area where an activity takes place, delineated by some boundaries. Now this is the same in physics. A field is an area where a force applies. There are three types of field at IB: the gravitational field, the electric field, and the magnetic field. These are three areas where a type of force would apply. We come across the idea again in science fiction films, where you can see usually that there is an area where a force is usually repelling or stopping something from happening. But the idea is a good one. In the case of a gravitational force, however, it's not so dramatic. A gravitational force is simply an area where a gravitational force will act. Here we have a section of the moon's gravitational field which affects the Earth. So what we've got is a space or an area where the moon's gravitational force has an effect on the Earth. So the gravitational field around a planet, or in this case the Earth, is often represented with these arrows. These are called field lines, and we'll talk about those a little bit later on. But as you can see, the field acts all the way around the planet or the Earth. In 3 dimensions, we could represent it. We actually represent it as more like something that looks like this: a steep slope, which concentrates or becomes much, much steeper as you get to the center of the planet. But this diagram is a little bit more complex, and we'll come to that later. So Newton spent a lot of time thinking about this gravitational force, and is in fact responsible for quantifying it, for coming up with a relationship. In his Philosophiae Naturalis Principia Mathematica, which he released in 1687, he was the first one to actually come up with a relationship for it, which moved away from this idea that gravity was something, a property of the material itself. Prior to Newton, ideas about gravity were pretty varied, but were pretty much based on this idea that gravity was innate in an object, that gravity was something an object possessed. And what he did is he took gravity outside of that, and he created this concept of a field. And his relationship is a very simple mathematical one. He came up with this idea that the force acting on an object, the gravitational force, is in fact proportional to the masses of the objects, and any two objects could attract each other with this gravitational force regardless of the size of this mass. He also predicted that the force was inversely proportional to the distance between the center of the two objects squared. Now the proportionality came first. So he came up with this idea of force proportional to the masses and force inversely proportional to r squared. This constant of proportionality came a little bit later, and we'll come to that in a second. One very important thing to note is the distance assumes that the masses do not have this size. We assume point masses. We assume that the mass of the two objects is concentrated in the center. So therefore, when we are measuring the distance between the two masses, we start from the center of the two objects. It doesn't matter how huge they are, if they're planets, stars, whatever, we always start in the center. Now, that's important to note in calculations where you're sometimes given the radius of an object and the distance between objects. So you have to kind of consider that the distance that's relative is from the center of each. Another important note about this relationship is that textbooks do not use common terms. Sometimes the two masses are represented as capital M for one mass. We assume it's a bigger mass, and small m for a smaller mass. And sometimes they're represented as M1 and M2. There's no formal way of writing it, so you just have to consider that there's two masses involved in the force relationship, so therefore one m stands for one of them and the other m stands for the other. But it doesn't matter. You can use whichever you prefer. So that's our proportionality. And as we always relate proportionalities to graphs, if you were to consider the relationship between force and position or distance r, you would have this great 1 over r squared relationship. Okay, now there's a really nice simulation here that you can have a go at, and you can actually plot this graph. I'm not sure we have time for that, but that is a nice activity to try. Now, what about this big G? Where did that come from? Now that's called the gravitational constant, and in order to find that, experimental values needed to have been taken. So it all came down to the work of Philipp von Jolly, a German physicist in 1879, who made this contraption. He developed a method of measuring the attraction between two masses. He used lead and these enormous great big spheres to try and get the two masses to actually attract each other. And then using a counterweight, he would balance and find the value of F. Now, by plotting the relationship between the forces and the distance, using that graph, linearizing it, you remember that from topic 1, he then came up with a value for the constant of proportionality. Here we have a photo of the 5,775.2 kilogram lead sphere that he used to actually do the experiment, which is insanely heavy. But our value of G is 6.67 times 10 to the minus 11, and it's called the gravitational constant. Okay, this is on your data booklet, but it's kind of easier to just learn it off by heart because you're going to be using it a lot. So that's our relationship. What I'd like you to do now, or pause the video, is to just practice using it. Let's try this example where we have the Earth has a mass of 5.98 times 10 to the 24 kilograms, and the Moon has a mass of 7.36 times 10 to the 22 kilograms. The average distance between the Earth and the Moon is 3.82 times 10 to the 8. Stop the video and have a go at calculating this value. Okay, by using that equation, you should have managed to get the right answer, which is 2.01 times 10 to the 20. I hope you got that right. So let's move on. Let's have a look at this idea of gravitational field strength. We came across this concept of gravitational field strength in topic 2, and we related this idea of G, which for Earth is 9.81, to the acceleration due to gravity. These two concepts, gravitational field strength and acceleration due to gravity, are equivalent. So the first thing to bear in mind is that if you are calculating the gravitational field strength, you are also calculating the acceleration due to gravity. Now, how do we define this idea of acceleration due to gravity? Because so far, or gravitational field strength, because so far what we said in topic 2 was that it was a measure of how strong the gravitational effect is on the Earth. And you can compare gravitational field strength of different planets and say, well, a greater value of G means that that gravitational force is much stronger. But now we actually have to officially define it using Newton's law of gravitation. Now, the gravitational field strength is defined officially as the force per unit mass that would be experienced by a test mass placed at somewhere in that field at that point. So if I have a field which is around a planet, in this case the Earth, and I have a mass inside that field of 1 kilogram, what would the force be on that mass that has 1 kilogram, right? So you can understand why the value of G is calculated by taking the force and dividing it by the mass of the object in the field. And that will give you the force per unit mass per kilogram of any object in that field. We can use the equation, Newton's law of gravitation, to give us another relationship for that. And in fact, this proof is something you need to be clear on. If G is equal to F over m, then let's bring in our relationship for force that we looked at earlier. If F is equal to gm m over r squared, if we divide that by the mass in the field, then we're left with a relationship for G, which is equal to G, the gravitational constant, times the mass of the planet, or the mass of the object that is generating the field, over r squared. Now, isn't it an interesting idea? Because you guys know that acceleration due to gravity is 9.81, and that's a constant value. But what we're seeing here is that it shouldn't be a constant value. G is 9.81 on the surface of the Earth. But as we move away from it, the value of G changes. We talked about this in topic 2. Now what I want you to do is just consider why that is. So I'd like you to stop the video and now calculate what would G be if R is 6,371 kilometers, and what would that G value be if you were 10 meters above the Earth? What difference would you see? Stop the video and actually work out G for a value of R which is equal to this value, 6,371, and then work out G if you change this for 10 more meters. Does it actually make a difference? G equals 9.81, good, and you should find that 10 meters makes no difference. So let's have a look at how we represent fields. To show the direction and the size of the fields, we draw gravitational field lines. These are field lines, straight lines that represent the direction of the force. Gravitational forces are attractive only, so you would draw an arrow showing how that mass would be attracted, and all the lines would join at the center because that's where the force is acting, towards the center of the mass. The distance between the field lines is very important. This diagram shows that the distance at the same height is constant. That means that for any given height, the value of G, the field strength, is constant. So you must show that by showing the same space for the same value of G. Thirdly, make sure that you show that as the value of G increases, the lines get closer together. The gravitational field strength is greater, closer to the mass, so therefore we show that these lines are closer as that value of G increases. Field lines must be drawn accurately in the sense that you should use a ruler and you should be very careful about these spaces. On the surface, we assume that the value is constant, and this is a uniform field. The lines are equally spaced out to show that the value is constant. Now that happens on the surface because at that distance, at very small distances, the value of G does not really change much. So therefore we demonstrate that by keeping the spaces pretty much constant. You should know both the radial and the uniform field diagrams off by heart.